Yo. If you want to follow along with this tutorial, you need to be on the branch all3 Vulkan Renderer init. Just a small disclaimer, I added a git ignore to every branch because I felt like that the main exe, elk, pdb and win platform obj files, they were cluttering the repository, and so I thought I would remove them. Okay, so last time we managed to get a window on screen and clear the color to yellow, but we still get validation errors every time we run through the loop. And when we close the application, we get a Vulkan error as well. And so I thought the next step would be to make sure that these errors disappear and to get a triangle showing on screen. So in order to do a triangle, we need a render pass. Let's just begin creating the render pass and then talk about what it's actually doing. I think that's easier. So we do render pass here, render pass. And again, we start by calling vk create render pass, and then we look what we need and supply that from bottom to top. And I think that's the easiest way to program in Vulkan. So we do vk create render pass. What do we need? Well, obviously we need a device, vk context device, a pointer to a render pass create info. This would be a pointer to rp info, allocator 0, and obviously a render pass pointer, vk context render pass. Let's create that real quickly. Put this below the swap chain, vk render pass. Back down here, we supply the vk render pass create info, rp info, initialize that to 0, rp info dot s type, vk structure type render pass create info. Nothing new here. Now it gets interesting. rp info dot. The render pass works with attachments and subpasses, and I think it's easiest to describe the attachments first. Pointer attachments points to a vk attachment description, and this could be, for example, color or depth attachments. Since, for example, we want to draw a colored triangle, we will need a color attachment. We don't need depth testing for now because we don't do any depth testing, but if we were to do 3D games, we probably would need that too. So let's just fill in the pointer attachments, which would be a pointer to an attachment, and rp info dot attachment count would be 1, like so. vk attachment description. Attachment, what is that? Need to spell that correctly. Attachment, let's see, attachment dot. This time no s type. In the attachment we have final layout, initial layout, load operation, store operation. And what this attachment will do is it will load an image, tell the graphics card what to do with the contents of the image and what the image layout will be. Then it will do its thing. I don't exactly know what will happen. And after the attachment is done, after the render pass has gone through this stage, it will transition the image layout into the final layout and apply the store operation. So let's do the load operation first. Load operation, which would be vk, let's do this proper, vk attachment load operation. And now we can specify, do we want to clear the image? Do we don't care what the image was? Do we want to load something? And those two I don't know. But I know that we want to clear the image. This will mean that in the render pass down in the rendering loop, we can say, well, clear color, and this will then clear the image to this color. So we specify clear here. Let's do the initial layout. And most of the time we do vk layout undefined, image layout undefined, meaning we don't know what the image layout is. Let's do the final layout. This would be the vk image layout, and this is what we want to specify that is telling us down here. This would be a shared present khr, or it could also be vk image layout present khr. And since we don't share this image, it'll probably be present, right? Then we go to attachment.store operation. And what do we want to do when storing the image? We can specify vk attachment store operation, and we can do the same thing. We can store the image, we don't care, and some other stuff. And obviously we want to store the image because we don't want to discard what we have done with the image. For example, if we have written to the image, right? So we want to store the result. We need more stuff, and that is, for example, the attachment samples. And this will specify how many samples per pixel we take around the pixel. vk sample count. And we can specify, do we want to have 1, 2, 32, 4 bits, 64 bits? And we specify 1 bit for now, but this is what you would do with multisampling, for example, right? This is where multisampling comes from. You have a pixel in your image, and then you specify, well, I want to sample around the pixel to blend in color, but we don't want to sample here. We just want to take the image as is and then present that. The last thing that we need, the attachment.format. And this is the same format that we specified earlier in the swap chain and for the images. And this is the VK context format, surface format.format. And this is it for the attachment. And it would be nice if that was it, but we can run the program and run into an error and then see what happens. VK check, like so, put that in, and then just put a breakpoint here, build the program, run that, go over here, and let's see what is happening. We get a validation error. And the validation error tells us that the VK create renderpass, pointer create info, subpass count, must be greater than 0. It is kind of weird how the renderpass works, and I don't really know why it is that way, but in Vulkan you have to specify subpasses. Those subpasses are more or less what the full render pass will consist of. You could have different subpasses to achieve different jobs. And when creating a render pass, you need at least one subpass and specify that. So we will create this one subpass and just supply the color attachment as a reference to that subpass, and so when the render pass is run, it will run this subpass for us. There's also more stuff about the subpasses in the render pass. You can synchronize between them, and so that they transition the image into different layouts between the subpasses. For example, the first subpass will transition the image layout into A, and then the second subpass will expect the image as image layout A and then transition that into B, and so you can chain those together. But we don't need that here. We won't even need that for dev, because you can just create the dev attachment and then supply that as a reference to the subpass. But yeah, anyways, I don't really know much about subpasses, and all I know is that you have to specify at least one, and that's what we'll do here, and that's what we will do here, right? We'll try to keep it simple. So yeah, in the render pass info, rp info.subpass count would be 1, and rp info.pointer subpasses would be what is called a subpass description. Pointer to a subpass description. That is a VK subpass description. Subpass description. Initialize that to 0. Subpass description dot. And this is where we can see all the attachments that we can specify in a subpass. We can specify color, def stencil, input attachments, preserve attachments, def attachments, and so forth. We want a color attachment, so we will supply the attachment for the color. Put the count to 1, subpass description dot pointer color attachments, which would be a pointer, and that is the weird thing, not to the attachment, but to what is called a color attachment reference. And that is a VK attachment reference. Color attachment reference. Initialize that to 0. Color attachment reference. We need an attachment, and this is an index into the attachments specified in the render pass info. This is supposed to be an array. We specified one element, so it will be the 0 index, but you could also, specify a def attachment, and then you have an array, and then you index those, right? The color attachment is 0. And there's one more thing, the layout. This is the layout during the render pass. And yeah, this is the VK image layout color attachment optimal layout. Nice layout, right? I can't tell you why this layout is supposed to be like that. I tried finding it out. I couldn't find out why. Maybe you can. I feel like we should make a small adjustment. The VK attachment description, call that attachments array, allocate that on the stack. Forgot the equal sign here. And then just supply the attachment. So down here we can use attachments instead of attachment and do array size of attachments. Don't forget the semicolon here. So if in the future we want to extend this, we only have to supply that in the array and don't have to touch this again. Build that and try. There's no validation errors, so everything's fine. Great. Obviously, we still didn't change the render loop, so we'll get all of that crap. But what we can do now is we can try to start the render pass in the render loop. So basically, when we begin the command buffer, after we begin the command buffer, we can do vk cmd begin render pass. Takes in a command buffer. Render pass begin info, rp begin info. And then the last one requires a vk subpass contents. I know this is an enum and we can specify null here, but there is only one value, which is vk subpass contents inline. There's also max enum and secondary command buffers, but we'll use inline. I've done a bit more research, and what that actually means is that the subpass commands will be recorded here. And what that means is basically when we do draw calls over here, this is the subpass running. And so these commands will be executed using this command buffer. If we were to use different command buffers, this is what is called a primary command buffer. We would have to call vkcmd execute, this vkcmd execute commands, which will take in our command buffer, and then a pointer to other command buffers that have the commands for our subpass. But this basically means we can record the commands for this render pass, for the subpass, and they will be executed. Okay, now let's do the vk render pass begin info, rp begin info. We initialize that to 0, rp begin info dot. We need an s type again, vk render pass begin info, rp begin info dot. So what do we need? We need a clear value count, and this is basically the clear value that we use down here, which will replace that soon. We need a frame buffer. We don't have one yet, so we have to create one. We need a render area and of course the render pass. The render pass is very easy. That is vk context render pass. The render area is also something that we can specify already. That is the vk context screen size. This is just the size of the window that we created, and we can query that. Let's do that now. In order to query the size of the window, we need to create a new file that will let us access platform specific functions, like querying the window size or opening a file or writing to a file. So we create a new file in source called platform.h. And inside here we pragma once first, and then we specify the function, which is a void platform. I will prefix every platform function with platform underscore to make it easy for me to understand what is calling where. Get window size. And that will take in a pointer to an int width and a pointer to an int height, because we will write those. I have to spell width. Don't know why this is complaining, but who knows. So back in our Win32 platform, we include the platform.h file, and then we implement the function that we specified. Void platform get window size. In order to get the window size, we can do a call get client rect. It takes in a window and writes to a rect, a pointer to a rectangle, the size of the window and the position. Let's just do a pointer to a rect, and then it's a window variable which is called rect. Spell that correctly, rect, and spell that one correctly too. What we can then do is rect.top. I just noticed we can't do pointer int but int pointer. That causes a problem. That is better. Copy that over. Now we need to get the rectangle, then we can do rect.left and rect.right. So we would want to do rect.right minus rect.left and store that value in the width, obviously in the value of the width. And then for the height, I have to spell width correctly. For the height, we do top minus bottom. Now the only problem is this window here. I don't want to have to supply the window to this call, because not every layer in the engine will have the window. So unfortunately, what I have to do is use this window as a global variable, just like the static bool running, like this. And so the platform create window will no longer need a window, meaning we have to turn every pointer into a normal window, and that should be fine. And then down here, we don't supply the window anymore. Then we can access the window over here and get the client rect. Now back in the renderer, the first thing in vk-init we do is platform gets window size. If I can spell, platform gets window size. Then we do vk context screen size dot width and vk context screen size dot height. And that would be pointers to those. Well, the screen size will be, put this up here, vk extend to d screen size. Extend to d has a width and a height, and that's what we need. And I guess now the function is complaining because it wants uint32t's instead of int pointers. We'll give them to the function, make sure the header is updated too. And now since the header doesn't know about these, it will complain. It is not a big deal because in Win32 we include windows, and that includes these uint32t values. But then again, I like to have my own defines file where I include all of those types, or maybe define them myself. So we'll create that real quick. In source, we create defines.h. The first thing we do is pragma once, and then we include cstdint. This will include all of those types that we need. I will also define a global variable, which is just static, because when I read my code, I like to know what my intention was when writing the code. For example, in the Win32 platform layer, the static, it basically means global variable. Those are global variables. Include defines.h here above platform.h. And therefore, the intention is clear, in my opinion, to anyone that is also not very comfortable with C++. Okay, so back in the renderer, we should have no complaints. We could try to run real quick. Oh, it complains that platform get window size should return a value. Well, because it's not a void. I forgot to change int to void when trying to find out what the problem was. Okay, that looks good. We could try to run real quick. It's basically saying that the frame buffer cannot be specified as a VK null handle. Yeah, that's what we'll do now. So we have the extent, which would be the screen size. And then I guess we need a frame buffer. Let's create that below the swap chain. Call that frame buffer because we need more than one frame buffers. In order to create frame buffers, we need to call VK create frame buffer. That takes in a VK context device, frame buffer info, FB info, pointer allocator, and a pointer to a frame buffer, which would be VK context frame buffers on I, because we need more than one. And I try to understand what exactly frame buffers are. The best explanation that I found is basically the metadata or the buffers used executing the render pass. But to me, this is not very clear what exactly that is, because we specify the attachments in the render pass and we then use the image views of the images from the swap chain in the frame buffer together. It's basically like this. You have memory on the GPU that is an image, for example. The image view describes what part of the memory you want to use. That would be the MIP levels, for example. Adds in the attachments together with the render pass and supplies this data to the render pass. I could be totally wrong on this, but this is more or less the best explanation that I got. But still not very clear, and I apologize if that doesn't help you very much. But yeah, so the VK frame buffer create info, FB info, obviously is a struct. Initialize that to 0, FB info dot s-type, VK structure type frame buffer create info, FB info dot. What do we need? We need to specify the height and the width of the images that we are going to use, and we store that in the screen size, so that will be easy. We need a pointer to attachments and an attachment count, and these would reference not the attachments in the render pass, but the image views into the images of the swap chain. And this is where we need the image views, because in Vulkan, we can't use the images directly. It is more or less memory on the GPU, and the image views describe how the memory is being used, looked at, and all of that stuff. So the pointer attachments we'll do in a second, but we can do the width with VK context, screen size.width, and do the same with height. The next thing we need is the render pass. That is very easy, VK context, render pass. We also have to specify the layers of the images. There would be 1, and the attachment count, we can specify that to 1 as well. We will use one image view, since we will have as many frame buffers as we will have images and therefore image views in the swap chain. So basically we do a for loop here. For UN32Ti is 0, I is less than VK context, swap chain image count, I++. We create a frame buffer. We could also do a VK check here. And in the frame buffer info, the pointer to attachments would be the pointer to VK context, SC image views on I. Now we need to create those in the VK context, and let's do this below the to do. VK image view, SC image views, 5 again. Second one is VK frame buffer, frame buffers. That should fix those errors down here. I have to spell this correctly though. Now that won't work out of the box, because we also have to actually create the image views. And that is what we'll do when we create the swap chain. We get the images and we also create the image views. Image views. We do that in a for loop. UN32Ti is 0. I is less than VK context. SC image count. I++. We call VK create image view. We take in the device. A VK image view create info. Call that view info. Allocator, nothing, and a pointer to image view, which would be VK context, SC image views on I, and obviously a pointer to that. We now have to specify the VK image view create info, view info, initialize that to 0. Obviously we need the S type VK image view create info over here, view info, dot. We definitely need to specify the image, but we don't do that here, which would be vk context swap chain images on I. We need the format of the images, and that's why we saved that earlier. That is the vk context, the surface format dot format. And for those that don't remember, it is this format over here. The next thing we specify is the view type, and that's how we specify how we want to use that image. And that is a vk image view type 2D, meaning we want to have a simple 2D image. And the rest is just some basic stuff. For example, the sub resource range dot aspect mask, which would be vk aspect mask vk image aspect color bit. Basically, we want to use a color image. View info dot sub resource range dot layer count is 1. We want to have 1 layer and 1 level. We specify the image in the view info, and then we create the image view. We can vk check that. Let's see. I think the pointer is the problem. Yep, that's fine. And we also have a problem further down here. We have to specify the vk context frame buffer on the image index. Renderpass. Try to compile that. That seems to work. I doubt that it'll work immediately. So let's just put a breakpoint in the render loop and see. Check if we get an error. We do get an error. We get an error that the corresponding frame buffer height is way too high. And I think that is because I don't do... Yeah, I need to do bottom minus top. I'm stupid again. Bottom, top. Okay, let's do that again real quickly and see if that throws an error. Nothing. Great. So we successfully created a frame buffer. We created the image views into the images of the swap chain. And then we can see if we can actually begin the render pass. And it doesn't look like we can do so. We get a validation error that the clear value count of 0 must be at least 1. And the pointer to clear values cannot be null, because we specified the vk attachment load operation to be clear, which is what I was talking about earlier. So basically what we need to do is we need to specify that over here. rp begin info dot pointer clear values. It is a pointer to a const vk clear value. That is a pointer to clear value. We can look at the vk clear value. That is not a vk clear color value. It is a clear value. That is a struct again. Clear value dot. We have color and def. We want to have color. And that is the same thing as before. We can specify in integers the color that we want to have. And that is 1101. And of course we have to do the rp begin info dot clear value count to be 1. And then down here we can actually remove those two and try building again. Run the program. Should be nothing in the debug console. No. Go down, begin the render pass, and that worked. Now the end command buffer has a problem. We don't end the render pass. So we have to do vk cmd end render pass, fix in the cmd. Now I will try to remove the breakpoint and let the application run and look in the debug console. So we get validation errors. It just took a while. We attempt to free the Vulkan command buffer that is in use. And this is because we don't wait for the device to be idle here. We can try waiting for the device to be idle again. vk device wait idle, vk context. Obviously, this is terrible in terms of performance, and we will change that later. But we'll just do this quick fix to see if it works. Seems to work. So we basically free the command buffer every frame. We allocate it every frame, and we get no validation errors when the program is running. That is great. Now, obviously, we still get this one error when we close the program, because it's telling us, well, the swap chain is out of date. That is okay because we closed the window. We will fix that later too. But we now have a render pass, and that will enable us to create a pipeline to actually draw a triangle on screen. If you like what I do, consider tuning into my Twitch. I stream at 10 AM Central Eastern Time, which is 1 AM Pacific Daytime. You can also support me on Patreon. I've set up a new page. Supporting means getting access to the game code that I'm currently working on, which is Cake's Tower Defense.